Hello there students, and welcome to Year 10 Science and the Motion and Energy topic. This is video number 5 looking at Newton's second law. When we looked at Newton's first law, we realized that Newton's first law just deals with the effects of a zero net force. There can be lots of forces acting, but if they cancel each other out and there is a zero net force, then we know that objects will not change their motion. They won't speed up, they won't slow down, they won't change direction. But when there is a net force, even if there are multiple forces, only one of which is slightly greater than the others, then we have a net force. We have an overall force. And when we work out the magnitude, the size, and the direction of that force, we can also work out the acceleration on the object, how its motion is going to change as a consequence. Moving objects will speed up or accelerate if the net force acts upon them in the direction of travel. So we can ensure that our car, for example, speeds up if we apply a force in the direction of its motion. So if it's already moving to the right and we add an additional force of 5 newtons, then we're going to accelerate that object towards the right. That means that it's going to speed up, or it's actually going to start moving if it's at rest, or if it's already moving, its speed will increase. Newton's second law states the acceleration of an object is directly related to the magnitude and direction of the force acting on the object and inversely related to the mass of the object. Newton's second law is most easily remembered by the equation F equals ma. This is because we can see that F is proportional to m, and F is also proportional to A. Or if we look at rearranging this equation, acceleration is equal to force divided by the mass. So I'm just dividing both sides here by m. Then you can see that the acceleration is proportional to the force. If this number gets bigger, this number gets bigger. But acceleration is actually inversely proportional to the mass. So that means when this number gets bigger, this number here gets smaller. These relationships are very important when we're analysing the motion of different objects. Friction is one of the forces that often acts as a resultant force to oppose the motion of particular objects. Any two objects that are in contact, surfaces in contact, can create a frictional force which opposes the motion of those, or at least one of those objects. So if we push a box along a floor, then if I apply the force to the box in the direction to the right, and it is sitting on a flat surface, then there will be a frictional force, a force due to friction, that will be opposing that motion. Now, provided the force that I apply is greater than the frictional force, the object will continue to accelerate in this direction. If I give the object a push and lose my contact with that box, then the only force that will be acting is the force of friction, slowing it down. So eventually the box will come to a stop. Now you may be thinking, well, there is another force. It's the force due to gravity. It's the weight force. And that, yes, that's true. That is also in application. But if it's sitting on the floor, then there will be a normal force which is acting equal and opposite to hold that box in its vertical position. So I can consider those two forces cancelling each other out and just focus on what's happening with the frictional force. As soon as I lose contact with the box, the only force acting is then the frictional force, contact between the box and the floor, and that will cause the box to decelerate because it's acting in the opposite direction, slow down, and eventually it will come to a stop. One of the important considerations of Newton's second law is this whole idea of acceleration and deceleration. As I mentioned before, acceleration depends on the net force and the mass of the object. It increases with the size of the force, but it it changes inversely with the mass. It decreases as mass increases. And this is one of the important things when we look at collisions later on. We're going to move on to Newton's third law and see the interaction of, say, a car and a truck during a collision. But one of the things that's very important is if the same force is being applied to a less massive object, such as a car, then it will have an increased acceleration. And this is one of the most important things we need to focus on as we look at the implications of Newton's laws. So a simple calculation then, if a net force causes a mass of 10 kilograms to accelerate at 2 meters per second, we need to calculate the magnitude of the net force. So Newton's second law tells us F equals ma. F is proportional to the mass and also to the acceleration. So if we have 10 kilograms and it's accelerating at 2 meters per second, then we have a force of 20 newtons acting. This is just a magnitude. You'll notice a couple of times I've done calculations on vectors, and force is a vector without a direction. When you're not given a direction, it's just saying it's accelerating. I'm not given a direction, so I just need to work out the magnitude. What I can do, if you want to be more physically precise, is to say in the same direction as the acceleration. Thanks for watching.